Okay, let's get started to lecture 3. What we'll see today is, so far the first 2 lectures we discussed sort of Hamming's problem while talking about coding theory. Today we will introduce coding theory from the perspective of Shannon. So both of them were trying to sort of model communication over a channel, or a potentially noisy, corrupted channel, and they came up with different ways of doing it. And over the course, we'll be following both the Shannon model and the Hamming model. So far, we spent on the Hamming model. What we do today is almost all of today's lecture, and possibly some part of next lecture, we'll be talking about Shannon's coding, and in particular, we'll be doing the in detail the noisy coding theorem and its converse. Yeah, so where's Shannon's? So where was Shannon's model come from? So Shannon was looking at this problem. So what was Hamming looking at? Hamming was interested, there was this magnetic strip where he could write, magnetic strip or punch card where he could write things on, and he knew that this would make very few bit flips, and so he wanted to model what's the best you can write on this. So Shannon was also thinking of something similar. Shannon was thinking of something in the following lines. So there is some source, and there's some receiver. The source is sending a sequence of messages which the receiver has to. Okay, this could be me talking over a telephone. It could be things being written on a hard disk, which is then read by somebody else, or it's a television and this is the antenna. No, so there's an intermediate channel. Channel, which does something with, so the channel is sort of the medium through which the source is transmitting to the receiver. The channel is not perfect, it has some properties. Now the question which Shannon was asking is, so suppose the source is producing information at some particular rate, the channel is doing something to this information, and then the receiver is receiving whatever the channel does with this information across. When can you actually be the receiver extract the information that the source is sending across? When is this feasible? What needs to be done for this? So the channel, it could be the case that the channel is perfect, the channel is imperfect, whatever. So his general question was, there's a source which is sending out information. There's a channel which is sort of doing something with the information and is getting something, sending out something else. Now, so this has some property, this has some property. When is it the case that you can do what this person intends to send can be received by this person? This is the very general question that Shannon was asking. So for the first thing, we need to first model. All of this is very, very general and it's unclear. So we will first try to mathematically model what a source is, what a channel is. More importantly for us, we'll be trying to focus on what a channel is. So when is communication feasible? That's the question which we wish to ask. And this is sort of similar to what Hamming did in some sense. The way Hamming modeled it was, he said he modeled the channel by stating the channel is something which does bit flips, possibly, but does at most t bit flips. Now can you handle it? Now similarly, but Shannon was going to, that was what Hamming did. Shannon was going to ask him, Shannon actually took a far more general setup. He would like to ask this question. So firstly, we'll have to mathematically model both the receiver and both the source and the channel. We would like to so the channel source, we think of it as so Shannon adopted the probabilistic model. Everything is randomized. Things have the source is producing information under a particular distribution. The channel is modifying what is sent through it based on some other probabilistic model. So Shannon was trying to model all of this via a probabilistic means, via randomized means. In fact, that's the main difference between how Shannon's modeling and Hamming's modeling of the channel differs. What it is this one? So Shannon assumes that the source is modeled by a distribution. So there's some underlying distribution, say P, from which the input is being produced. So X is being sampled from P. So that's the input, and this being produced at a steady rate. It keeps on sampling. It produces X1 according to P, sends it across. X2 sends it across. X3 sends it across. This is this one. And you wanted to capture what this one says. So you find something called the rate. You want to fully describe this. This is what, and trying to understand what the rate of it was when he defined the entropy. The notion of entropy. So if you have done information theory, you'll know what entropy is. So given a distribution, what he captures as rate is exactly the entropy of this distribution X. So we define it for specific distributions. I'm not going to define it very generally right now. So this is how he captured so the mathematical, this one which he did was this notion, the source was captured by a mathematical quantity called rate, which was exactly what is the entropy of the distribution. And this entropy is a quantity which Shannon defined. And what about channel? The channel, what he wanted to say is there's some input X that's fed to the channel. It gives out some Y. So he will assume so what Shannon will use, this X is the input alphabet of the channel and Y is the output alphabet. So now let's assume, for simplicity, almost all the time we'll work with channels in which the input and the output alphabet are finite alphabets. We can think of infinite or continuous remains. We will never study them. I might give some examples here and there. And how did Shannon model this? Once you say for every input alphabet, the channel produces a distribution on Y. It's going to sample. So basically, it's given by this sort of input out. The channel is modeled for every X in X. There's a distribution which is the conditional pi, which is Y of X on the output channel. And that's basically stated. Let's call it P of X on the output channel. And basically, if you send X, the channel produces a Y which is distributed according to. If you send a different X, it's according to the different. If you send X prime, it's going to be according to dx prime. So, if you want to ask what is this X and this Y, this is exactly, this happens with probability dxy condition on P of X. So P of X is which X is being produced by the source. So this whole thing happens, X is being produced by the source, then the channel corrupts it with VFXY. So this pair XY appears, this is the probability with which it appears. Okay. And a couple of things. Shannon is going to have a thing called a memoryless channel. That is what, so you can ask this. So told you that the source is producing X at regular intervals. It's sending an X, the next X, the next X, constantly sending things out. Now, how does a channel act? The channel could be taking all these X's and takes this whole vector of X's and produces a vector of Y's at the other end. It could be correlating one. For simplicity, we'll assume that the channel is sort of memoryless. It takes the first X, produces the Y according to this distribution. Takes the second X, produces the Y according to the same distribution. So each instance it does it separately. That is, there's no memory carried across the instance. The instance could be more, the channel could do things in the sense the way it corrupted the first one, it could use that information to way it corrupted the second one. For example, Hamming's model does take into account this. Hamming's model had in the first, if you're sending n bits across, if it manages to have corrupted t bits already, the next things it should not corrupt. So Hamming has to keep this track. Hamming's model, Hamming does it, it's not a randomized model, but Hamming is not a memoryless model. It needs to keep track of how many corruptions it has happened. So in particular, if you're sending x1, x, so what I'm claiming is there's a y1, y2, yn times x1, x2, xn. This is just going to be product of d of xi, ys. The probability that you see a output y1, y2, yn when you send an input x1, x2, xn is exactly this quantity. So I equals 1. So this is the memoryless assumption. So this is an assumption we are making on while modeling the channel. That is, each time the corruption happens, each time the channel distorts the message, it sort of does it independently of how it did it in the past. Okay. So let's actually, to get our hands of it, this one, let's actually see a few examples of a channel before we proceed further. So let's examples of channel. First called the BSC channel. It's a binary symmetric channel. Stated probability P is usually denoted by BSCP. P is some number between 0 and half. You can think of P being larger than half too, but then you can just flip. You'll see that it's actually symmetric. You can model it just by what is the BSC. And here both the input and the output aspect are the Boolean. It's 0, 1. And this, and this, I give you a 0, I give you a 1. So what happens with probability 1 minus P? With probability 1 minus P, 0 is transmitted exactly as a 0. With probability P, there's a flip, there's a crossover probability that happens. And you get a 1. And it is symmetric of behavior of 1 is exactly symmetric. This is 1 minus P. Okay. Notice if P is half, this channel completely destroys your message. So there's no information because basically then it's ignoring what the input is and just sending you a random point. So P half, the binary symmetric channel, is that basically it's ignoring the message and just giving you random bits. But for every other P, there is some information that the channel is giving based on information. P could be less than half, P could be more than half. P is more than half, you'll just flip the input and output alphabets and view 1 as 0, 0, 1. So we'll talk about BSC only when P is 0 half. In fact, most of the lecture today, all the formal theorems we'll be proving today in Shannon's coding theorem will be with respect to BSC. We won't prove it for the general channel. We will define what a general channel is. This defined in terms of these conditional distributions. Shannon's original paper, The Mathematical Theory of Communication, sort of invented the field of information theory. Coding theory does talk about general channels. And he takes specific examples, one of the foremost examples being the BSC. Okay. That's the BSC channel. Next, another commonly studied channel is the binary erasure. epsilon over here, which should be EC epsilon P. So here the input alphabet is 0, 1. The output alphabet is 0, 1, and there is an erasure symbol. So what's happening is going to be there are going to be two input symbols, three output symbols. What? And the probability 1 minus P, 0 gets transmitted as is. The probability P, 0 gets smudged.
Prahladh, you call it epsilon.
And the same, and it's symmetric. That's the binary arrangement. So if you see a bit in the output, you know that is the original bit. Sometimes you might see a corruption, you might see an erasure, you might see a smudge. It's not as if the smudge disappears, you see a smudge. So you do see in the output, you see a 0, 1 or what. If you know what, you just know that something has gone wrong with the channel that you have to somehow recover. So this is this sort of captures the binary erasure channel when sometimes in the channel just says fail that I don't know how to make it. So this is sort of incorporating that model. So these are sort of the two most widely studied things. You can of course extend these to, you can extend the binary symmetric channel. Right now it's on the binary alphabet. You can extend it to the query alphabet, in which the probability 1 minus P you output the symbol uncorrupted, and with probability P over Q minus 1, you pick a random this one among the remaining Q minus 1 symbols and output it. That's so you can define the corresponding query symmetric channel to be of the same form. There's something called the noisy typewriter channel. In which it's sort of trying to, there's one way of modeling the old typewriter, that is so every key, most of the time when you type the key, you happen to type the right key. So you think of the alphabet as say A to Z. Most of the time you type the right thing, but sometimes you type either the left key or the right key. So there's a probability P with which you output, there's a 1 minus P probability with which you output the same alphabet, with the probability sort of P by 2, you output the alphabet to the next alphabet. That's what happens in the typewriter. But sometimes the typewriter is usually just even further simplified, you just work with say some alphabet of size. So X is Y is say some alphabet of size M, or say size Q. Size, and what you say is each one is transmitted correctly with probability 1 minus P, and there's a probability P in which it outputs the, so this is I plus 1. So it's sort of like you either output yourself or the guy adjacent to you, and it's sort of right now modeling it as if it's only this one guy adjacent. So one way of doing this is usually you simplify the fact that the typewriter has two things adjacent to it to make one, and this is a noisy typewriter channel. Okay, and you can ask under this what is. So you see a piece of text, things you get corrupted every now and then this way. You still want to be able to read the English text. Perfectly fine. So you can, this models various sort of channels. And just an example of a continuous channel, which we will talk about, is called the binary input. The input is binary. With array 2 Gaussian noise. What is this? The input is say 1 minus 1. I want to keep it symmetric. But I'm going to make the output the real alphabet. The output is going to be reals. What does the channel do? It's the input you get x, which is either you get a bit either 1 or minus 1, and then you pick a Gaussian with standard deviation sigma centered around your either 1 or minus 1. You pick a Gaussian, sample a point according to that, and send that across. Okay, so probability of y given x is exactly what is 1 by 2 by sigma e power minus x minus y whole square by 2 sigma. That's
Sigma will be also.
sigma is also. This is a density function. This is not the probability function, the density function. Yeah, so this is also studied sometimes in practice. We will, I don't think that we do any theorem with respect to this. What did, okay, these are examples of channels and stuff. What did Shannon sort of do? Shannon put the following very general meta theorem. With every channel, he associated a quantity called the capacity of the channel. In fact, he told you how to compute this channel. It's possibly not efficiently computable. He showed how to, for every channel, he associated a number. So for all channels, so now when I mean a channel, I just mean a conditional distribution. That is, a channel is just an input alphabet and output alphabet and conditional distribution. So actually, let's make it memoryless discrete channels. This is going to be an informal statement. Yes. Discrete means the alphabets are both finite. The alphabets are discrete channels. That there exists a number C, which he refers to as the capacity of the channel. Then 1, if rate of source R satisfies R less than C, then he says there is a way to actually transmit it so that you can then what he says is there exists an encoding function and a decoding function. What does he mean by that? What he means is we had this original picture over here. If there is an encoding function and a decoding function, okay, such that the source, you take it, the encoding functions modifies the source and then transmitted this encoded symbol instead. So this is M, this is E of M. The channel is going to now sample from D of E of M and output something. So it's going to output a Y, where Y is distributed from D of E of M. And this decodes it, then produces an N prime, such that the probability that M prime not equal to M is, basically he said, as for every channel, there's a number called the capacity, as long as the rate of the source is smaller than this capacity, there is some encoding function and decoding function such that you can transmit it, so that no matter what the channel does, you will be able to recover the original message effectively. There will be a very small probability of error. So this randomness is over multiple things. This randomness is over the randomness of the source. It's also the randomness of the channel. Right now, I'm assuming the encoding and decoding functions are deterministic functions. Okay, but that doesn't justify the name capacity. Furthermore, he shows if R is larger than C, then actually you cannot produce any encoding or decoding function that will do this. And if R is larger than C, then for all encoding and decoding functions, no matter which encoding or decoding function you give me, there will be one message M. There exists one message M for which probability M not equal to M prime will be very close to 1. That is, you will almost surely make an error. That is, if the C is this sharp threshold, up to which point you can, as long as the rate of the source is less than this capacity, you will be able to transmit information without making, such that even though the channel does some fudges with the thing, the encoding and decoding together will be able to extract the information more or less faithfully with very high probability. If the rate is larger than this, then no matter what you do, you will never be able to record. There will always be a message which is completely corrupted. So you have to drop off that message. Once you drop off that message, so sorry, I don't want to say there exists a message. I just want to say there exists a message. This is over once again. Probability M not equal to M prime. This is over the randomness of the source. Let's just write it this way. Probability error. That's fine. Here also error will be close to it. So it's a sharp threshold. When the rate is less than the capacity, there exists some encoding. He doesn't specify how to get this encoding, and this theorem does not specify. We will see this. This is where this is one of the big places where Shannon and Hamming are going to differ. It doesn't specify how to get the encoding decoding. There is an decoding function such that the error will be negligible. Once you go on the other side of this number capacity, no matter which encoding and decoding function you use, the error will always be close to 1. So usually this is in information theory. This is stated as form of two different theorems. There's one called the noiseless coding theorem and the noisy coding theorem. So I'll state both those versions shortly, both those interpretations. So one is called the noiseless. Coding theorem. I'll be sort of informal and hand-wavy for the first 10 minutes or so, and then once we will then get to the BSc, and then I'll make everything formal and I'll give precise statements. So the noiseless coding theorem. So notice now the way Shannon modeled the source and the channel, there was randomness both in the source and in the channel. So these two theorems are basically stating that the noiseless is one, the channel is not, makes no this one. The channel is the identity function. It does things uncorrupted. So the channel is noise-free, noiseless. That is identity function. It transmits identity function. It transmits every input faithfully this way. Now the question is, what Shannon now asks is, you want to send this message across, can you come? This is more usually called a compression thing. Now you can, if you know there's a distribution on the source, you need not send the original source in its raw format. You could sort of compress it. What Shannon's theorem is usually said is when is usually this theorem is interpreted as when is compression feasible. So he's going to compress the source. The noiseless theorem states. This is called the coding theorem. This is usually called this noiseless is called the source theorem, source coding, because the coding is happening at the source. The source is the one which is in this one. Then there's the noisy coding theorem. Here is the other end. Now, so here I removed all the randomness from the channel and put only the randomness in the source. Here we'll assume that the source is just the uniform distribution on the alphabet. There is no compression possible. It is the distribution with the largest entropy on that source, and the channel has its. So here you assume the source is incompressible. That is uniform distribution on source. And you're asking when is, so you have the source is a uniform distribution on say m messages, and you're asking when can these m messages be sent, when does there exist an encoding and decoding process so that they can be sent across the channel and received faithfully by this one. So when is this is more viewed as when is transmission feasible. When is transmission feasible? When is communication feasible? Despite so the meta theorem, when stated this way, is answering this question. Stated that way. So the way Shannon actually proves it, he proves the noisy coding there, and this is called Shannon coding. The coding is happening because of the channel. And the way the meta, actually Shannon proves both these theorems separately, and then the meta theorem is got by combining these theorems. Meta theorem is obtained by noisy plus noiseless. All of this has been very general. So for this course, we will not be doing source coding at all. All our thing will actually come with this is usually that will be done in information theory. And most of you would have seen this. If you have done information theory, you would have seen a proof of this, and that's done in information theory. What we would be more interested is the channel coding. The channel is the one which is adding noise to the whole thing, and we want to understand what we can transmit. Okay, and we won't even go do the more general setup of Shannon. We'll focus very specifically for the rest of the lecture on the BSC model. So for the rest of lecture, the remaining lecture, noisy coding theorem. Or this. That's the major. And now from now onwards, I won't do any hand waving. It actually will hand wave, but I will hopefully I'll hand wave the fact that you don't notice it. So here actually in this case, given BSCP, so notice that Shannon showed that there's something called the capacity of a channel. So here we'll have to exactly specify what is the capacity of the BSC channel, and the capacity of the BSC channel We'll see it in the consequence of the proof, but I will introduce the function BSCP channel. Is 1 minus h of p, h2 of p, where h2 of p is the following function as p log 2 of 1 over p plus 1 minus p log 2 1 minus p. This is which we call the binary entropy function. More small h trouble. Okay. I'll drop the 2 if it's this one. In general, we'll refer to binary. You can define a corresponding notion of the binary entropy channel of the entropy channel when you're working over the QRE alphabet 2. And why do we work? Why does this will actually turn out to be the capacity of the BSC channel? We will actually prove this, that this is the sharp threshold below which you will be able to 1 minus the binary entropy will be the sharp threshold, below which you will be able to, as long as the rate is less than that, you will be able to send information. There will exist an encoding and decoding process, and above this, you will not be able to send anything. Why does this number? Why does H2P? Why do we study this quantity? So notice that we are looking at binary. This basically happens because when you take take an input, say x1, x2, xn, and you send it to the BSC channel, it makes it sort of x1 plus e1, x2 plus e2, xn plus en, where each ei is distributed according, this is equivalent according to the, this is the Bernoulli. The Bernoulli P distribution. And this addition is happening in GF2. Do this way. So in general, what will be if you look at an n-bit string, what will be the typical number of errors, flips that will happen? NP, this will be the typical number of errors. And if you send the string x1 to xn, you're likely to be in anywhere, typically you're likely to be in this bar. So most likely you'll be in this. If you send the string x bar, which is x1 to xn, you will be in this. You will be in this sort of shell. Invariably, if you send x bar, you will be, this is sort of, think of this as this is Pn, this is P plus epsilon n, and P minus epsilon. Invariably, the message will be in this shell. That's, you can show it by Charnock bound, you will be in this shell. So you're interested, so many a time when you study this, you will be looking at volume of, remember, with volume of the n ball of radius Pn. Something or P plus epsilon n is a quantity that will come, and Hpn exactly is a number which is going to be a proxy for this quantity. So Hpn, the first thing we notice the claim, okay, volume to npn. This is the upper bounded by 2h. That's one of the reasons. And we'll also see shortly, it's a very tight upper bound. This is not just an upper bound on it, it's very close to, you can also prove a very similar lower bound. So let's quickly see this. This is the reason why HP will turn up in the proofs. This one. What's the proof for this? Let's let this is volume 2 in PN by 2 HPN. What is this? This is summation in choose J going from 0 to Pn. That's the volume. What's the this one? So recall HP was this number P log 1 over P 1 minus P log 1 over P. So that's roughly like P to the, if we can write as log of P to the P times 1 minus P to the 1 minus. So this whole thing, this whole thing will look like P to the Pn 1 minus P to the 1 minus. Like that. I'm going to write this as, let's pull out 1 minus P to the N, which J equals 0 to Pn, choose J, P to the 1 minus P. Right. Now, by the way, this is for PV interest only in P between 0 and 12 pounds. So when P is between 0 and half, what is this number? This is a number which is always less than 1. Therefore, if I certainly upper bounded by this quantity, I can replace Pn by J. That will only make this large, because this is because P is less than half. But with the P1 minus P is less than 1, and hence I can do this.
Summation is still until Pn.
Summation is still Pn. That's I'm going to put, that's also an upper bound. I'll just put it out there. So what will you get this to be? This is just going to be 1 minus P to the power n times 1 plus 1 minus 1 plus P1 minus P to the power n, which is 1, which is what we wanted. So I made two this one. Here I increase the summation from Pn to n, that's one. This one, and the other one, if I replaced Pn by J. Both are upper bounds, they're valid upper bounds for this. So this is a very useful claim to keep. And I want to say this is also not too far from the other claim which we will encounter keep, is the fact that volume 2 Pn is also greater than 2 HPN minus a little over. So this is just off. So that this is a fixed for every constant P, HP is a fixed constant number. So that's a constant times n minus a little o n times. Okay. So for large enough n, these two are more or less similar. And it's because when we deal with the BSC thing and all, we will frequently encounter these sort of balls and shells, have to look at their volumes. That's why the HP number will come out from these rules. Is this true? Yes. I'm going to be a bit fast on this proof. I don't want to do the calculations. But so, for example, it's easy. So you can do this by multiple ways. You can just the proof of this just follows by this. Just write volume 2 NPN is certainly at least n choose Pn. That's one of the terms, and it's the largest term. And you can show that just this term is at least so much. And you use just Stirling's approximation for factorials and get this. You can do something, you can do either Stirling's approximation. So you can show this is greater than or equal to 2 HPN. We either use Shannon approximation, or you can use more the first principles also. You can just use instead of Shannon as a much nicer approximation, you can just use this approximation. M factorial is sandwiched between m power n plus 1, e power m plus 1, and m power m. You can use this approximation also to do, and this is obtained from just this, the fact that integral ln x between 1 and x is sandwiched by the upper integral from 2 to m, 2 to m, summation by going from 2 to m ln m, and sandwiched in the lower side by going from 1 to m minus 1. You just, because the integral for ln is sandwiched between these two. Yeah, whether you found the curve from above or on the curve from below, you get these two bounds. You then, from this, you immediately will get this fact, and you can plug this in and you will get plug. And so you can use either Stirling or this Stirling approximation for m factorial, or even for the cruder this approximation. Either of them will, you can get this, you can eventually get the same. So this just tells you that in general we will have these volume of npm. We're interested in volumes of balls which have radius pm in the n-dimensional space in the 0, 1 to the n. They will typically, they will in general replace them with 2 to the power hpn in all our proofs, and that's where the binary entropy function will keep arising. It's the sort of the number of flips that you expect to see when you toss each n points according to the Bernoulli distribution. Okay, let's go to the coding here. Might be coding here one direction of it, and all that story for. So might be coding here. It says for all p, for every with BSC, so for every BSC between 0 and half, and for all epsilon between 0 and half minus p. So that's, I'm going to perturb p by an epsilon, so I want p plus epsilon also to be less than half. That's why I want epsilon to be between 0 and half minus p. We say that there exists a delta and an n naught, such that for all n greater than n naught, basically what is this saying? You have B, so I give you a BSC. I give you a BSC channel. What's the statement? I give you a BSC channel, and I'm going to tell you how much is the rate less than the capacity. Epsilon is going to quantify how much is the rate. So we said R is less than capacity. So R epsilon is going to be the fudge factor between the rate and the capacity. So I give you the BSC channel and I give you the fudge factor. How much less the rate? How much is the rate quantitatively less than the capacity of the channel? Then I say that for all sufficiently large n, the delta will capture the error. This one, there exists a k. K will be typically 1 minus hp plus epsilon times n. It's the ceiling of this. It's the floor of this, and encoding functions e 0, 1 k to 0, 1 n. So you're going to take n k bits this way. So you're going slightly, so the rate is just a little bit less than 1 minus hp. It's 1 minus h of p plus epsilon. So I'm technically have to add epsilon outside This is a continuous function. HP plus epsilon is something like HP plus epsilon prime. So I'm going to put it inside. So one thing which I should have said, which I didn't, this is binary entropy function. If you plot it, 0, 1, it's sort of a concave function, symmetric about half. This is not really symmetric, but it is, think of it as symmetric. At half, it takes the value 1. That function, if you notice at half, it will exactly be half log 2 into half log 2. That's log 2 will be taking base 1, so that will be 1. Exactly this one. When p is 0, there will be nothing. It will be 0. If this is symmetric about half, you can see that by definition it's symmetric. So that's the sort of the curve of this function. Right. There's an encoding function and an accompanying decoding function. 0, 1, n. So the encoding function is going to take a k-bit string. It's going to output an n-bit string from it. The decoding function will give an n-bit string. It's going to output either a k-bit string or it's going to say, I fail. It's going to give up. This is not the encoding of any message that I think. But the probability of, now you pick an m, which is m1, m2, mn, uniformly at random from 0, 1 to the k. You just say, you pick an m-bit string uniformly at random from 0, 1 to the k. You pick an error from Bernoulli P n times. So E1, E2, En. You take the message M, you encode it, E of M, then the channel adds noise to it, then you decode it. The probability this is not equal to M is less than or equal to 2 power minus 4. So that's the whole, that's the noisy coding theorem and all its going from. So it says for every BSC channel and every fudge factor, for every R which is smaller, that's so R is smaller than 1 minus HPN is exactly the rate, the channel capacity which I had mentioned. You take anything smaller than it. So P plus epsilon will be smaller than it. And for any k smaller than it, in particular, you can go all the way up to k this point. There exists an encoding function and a decoding function such that you can transmit this message with very negligible, but for negligible probability, despite the errors being added by the channel, the decoding function will recover the original message correctly. Okay. Yeah, it took a while to write this thing. I hope you never have to write such things. Statements in, of course, one week. With this. Okay. Stare at the theorem and tell me, is it possible we follow what the theorem is? It's quite a wordy theorem. And hard part is only the statement of the theorem. The proof is actually, now in retrospect, it's a fairly simple proof. It uses one of the very powerful techniques, which I do not know if you've seen in the, you might have seen in the MFCS courses. And the basic courses. So what we have to show, we have given this, basically we have to show there is an encoding function and a decoding function. What does the encoding function come up with? The function is encoding function. So what is the suitable encoding? This is what we need to. Essentially, just pick a random. That is for every message, just take the random n-bit string as its image. And do this independently for all the 2 messages. So therefore, in other words, for each m, pick the properties. And by the way, this is one of the earliest applications of the probabilistic method. So Harsha was sort of credited for the probabilistic method. This is Shannon is not too far. This is 1948. The Shannon's one. He just says pick an E randomly. What does that mean? For each m, 0, 1. Okay. Pick E of m to be a random n-bit string and independently across. That's the encoding function. Of course, you might ask some 2m's might collapse and all of that is all going to go in the probability of that. Basically, what we'll show is we'll take that whole function, we'll also put the probability over E and show this. So if it's probability over E, there exists one E for which this is true. So first we will just choose that. So there's a slight, this is one big difference between Shannon and Hamming. Shannon just says there exists an encoding function. He doesn't give an explicit encoding function. Whereas with Hamming's this one was a very explicit function. I told you these are the parity bits, this is how I get it. All of this. Shannon does not do this. All of Shannon's work is he shows there is a good encoding function. We don't know what's the encoding function. And that will be generally a problem with the Shannon sort of this one. We will show that the random ones work. It will be hard to find an explicit one. In fact, it's for long to open whether you can come up with a function that matches Shannon. It was, you might have heard of these polar codes recently. It's only then when actually we came up with sort of more or less explicit things which matched Shannon's coding theory. Okay, if that is E, what is D? What's the decoding function? How should I define this?
The nearest code word.
Well, yeah, you can pick the nearest code word. To make up, that's one way of doing it. I'm going to make my life a little more easier. So what I will say is, so if you give, so I'm now given I'm given a y in 0, 1 to the m, and I need to say what dy is. So 0, 1 to the n. So typically how many, so what do we expect it to be? We expect it to be in the p in a p ball around it. So we'll have add some, we'll put some p plus epsilon by 2. So we'll ask, is there a message which is obtained? Is there a message that is obtained by so let's draw a p plus epsilon by 2. So let's take so I'm going to take y. Take y. And let's draw a p plus epsilon by 2 n ball around this. And check how many messages are there so that the encoding of the message falls within this ball. If there is a unique one, answer according to it. If there's none or more than one, return what. It's a little different from this one, but this will be more convenient. We could work with what you said also. So it's basically if there exists a unique m such that delta em and y is less than p plus epsilon by 2 and return m, else return what. But I don't know why I'm writing this code, but it's yeah. If this one, then it's m, else it's
Won't you look at the epsilon scale and in the instead of epsilon bond?
what?
So don't, for example, if there is some code word that is very close to y,
Yeah.
if the distance is much less than infinity, can we say that with high probability this was not sent for?
Most likely, yes, but yeah. So you could actually, so the likelihood thing will actually, what you if you go follow what Prahladh, that's what will happen. I'm going to put this also. The point is the shell. The reason it will be that the shell and the ball, the most of the volume of the shell is that ball is actually in the shell. So whether I put this or that will not make a big difference. The volume of the ball more or less is going to be in the shell. Okay. So that's the decoding function. And you want to show that this encoding and decoding function actually work. Okay. Yeah, so the hard part in Shannon's coding theorem was actually the statement and realizing that it's this, the importance of this number. Once you do it and then once you know you're comfortable with the probabilistic method, the rest of the proof is actually fairly straightforward. At that point of time, probabilistic method is not as popular as it is these days. People are not comfortable. So then it's still a non-standard thing. But let's continue with this proof. So how do I want to finish this proof? I'm going to define a couple of bad events. So basically, what do we now need to show? We need to show this encoding and decoding function. We're going to show that this is satisfied. This is, but there will be further probability over the random choice of E over here. And we will show it for a random E, therefore there will be one E for which it is true, and we'll be done. So bad events, I'm going to define two types of bad events. E1 is this one that there are too many errors. That is, summation EI is greater than or equal to P plus epsilon by 2n. So that's after it is too many errors. The number of errors is more than what the channel happened to add too many errors, in which case I'm going to sort of say fail completely. E2 will be the sort of thing is this message was a bad message in the sense this message and the channel's corruption, this pair was together bad in the sense that there existed another message which was too close to it. So basically it's a bad, let me first write what it is. There exists an m prime which is not equal to m such that delta of E m prime and E m plus E is less than E plus epsilon by 2. That is M and E are a bad input message noise. Now notice that if E1 and E2 don't happen, if E1 does not happen, E2 does not happen, then I claim you'll decode correctly. Because if E1 does not happen, the number of errors is less than P plus epsilon by 2. Therefore, Y is within a P plus epsilon by 2 ball of EM. And this says there's no other message, therefore the decoding will decode correctly. So it's an easy observation that not E1 and not E2 together imply that decoding is correct. That is D of EM plus E will actually be equal to and C. Therefore, hence it suffices to count probability that E1 or E2 happen. That's the upper bound on the error. If both of this doesn't happen, then you know that you have decoded it correctly. Probability E1. That's just the Chernoff count. E1 just says, because what's E1? E1 was the event that summation EI is greater than P plus epsilon by 2n. You know the expected is Pn. This is just a Chernoff bound. So probability of En is less than or equal to some exponential in minus some C times epsilon square n. This is just Chernoff. What about probability of E2? It takes some amount of work. So what is E2 again? Let's start at E2. E2. So this is the probability over the choice of E and the noise error E. So let's write it this way. It's the choice over the encoding function and the error function such that there exists an n prime not equal to m such that delta of E of m prime is that's the probability which we want to compute. So let's do this in stages. Let's fix m e. Let's fix a particular m and e. So I fixed a particular message. I also fixed a particular error pattern. And now and also an m prime not equal to m. So the probability is now just going to be over the choice of m prime. So E of m prime, notice, is a completely random. So I fix m. Let me further fix even E of m. I fixed the message. I fixed the encoding of the message. I fixed the error. And I also fixed an m prime. This one. The only randomness I'm going to allow is the random choice of m prime. And I'm going to ask, what is the probability that delta em prime em plus e is less than p plus epsilon by 2 n. What is this? So what's happening here? This is right. The actual probability is over the even there's a randomness over e, there's a randomness over e of m, there's a randomness over e, there's a randomness over e of m prime. Right now I'm going to fix this object. I'm going to fix this object. So only object I'm varying is e of m prime, and I'm asking over this. So this is a fixed object, and I'm asking, how is e of m prime picked? You just pick a random point in the random n-bit string is chosen to be. Now I'm asking, what is the probability that this random n-bit string happens to fall in a ball with a radius p plus epsilon by 2? This is exactly volume of 2n p plus epsilon by 2n by 2 power n. And by what we seen before, this is exactly 2 power n into 1 minus h p plus epsilon by 2. Okay, because then upper bound on this. Sorry, am I going the other way around? So there's a minus. Yeah. The upper bound on this is 2 power h p plus epsilon by 2. So this is exactly this quantity. So this is where all the hp is going to take its. So for a particular m prime, this is the case. Therefore, now I can ask probability over there exists an m prime such that delta em prime em plus e is less than e plus epsilon by 2n. This is, I'm going to do it over random points of e power n prime for all n prime not equal to m. By doing this for each one of them, therefore this is just the union mode. I'm going to just be one. This is at most 2 power k times 2 power minus n 1 minus h t plus epsilon. Fair enough. That's the number of messages. I set it to power k minus 1. I'm going to ignore that. What was k? K was a number. So look at this. K was not too large. K is this number. K is smaller than 1 minus ht plus epsilon. Therefore, go back here. K is 1 minus ht plus epsilon. This is 1 minus ht plus epsilon by 2. Therefore, all you will get at the end of this is 2 power h t plus epsilon by 2 minus h t plus epsilon. And what is this? Once again, if you look at this curve, that's one for p is some number over here. We are looking at p. This is p plus epsilon. This is p plus epsilon by 2. So that will be a slightly smaller number than this. It will be a function of epsilon. You can show it will actually, it's actually a function of epsilon square. So this will be some function of epsilon this one. So you will get that, and it will be a negative function. This will be negative. That's the main thing I want. So this is less than or equal to 2 into some function of epsilon times n.
And
yeah, actually speaking, you can make it uniformly on epsilon. Right now, for us, let's make it. It's fine if it's. Yeah, that's the whole thing. So that's this is one error. That's the E1 is the other error. So E1 was an epsilon square that came from Chernoff. This one. This is this error. You just choose delta. Choose delta such that 2 power minus c epsilon square n plus 2 power minus f d epsilon n is less than or equal to 2 power minus. And you get this. There's a lot of calculations, but this is fairly actually. It's once you realize what's the number HP, it's basic. And why does HP come? Why does HP come in the proof? Because when you do this union bound, you get a 2 power h p plus epsilon. Therefore, you needed this 2 power h p plus epsilon to just be able to compensate it, and that's where the rate this comes.
So proof was not given by Shannon.
Huh? The proof is by Shannon.
But in the you mentioned that he didn't give exactly.
No, for BSC he will do. For BSC is explicit. For other channels he will. It's not a. So he will. The capacity is not even for certain other channels. We actually to this day we don't know what the capacity is. He will say there is. He will give you a formula for it, but it's not a formula that's efficiently computable or any such thing. It's mutual information. It's defined in terms of mutual information. So all of these quantities entropy mutual information were sort of defined by Shannon for exactly this, answering this question. For BSC, we know it exactly. This one, for other channels, it's not. Shannon's theorem is far more general. He takes his statement is true for every channel, he will identify a number C, such that if the rate is less than C, then there always exists an encoding and decoding function, such that the error is negligible.
And it works for infinite alphabets.
Not the way I have stated it. I think the way I stated it is discrete algebra. So you have to, so infinite, you have to be a little careful with this. Here, all the proofs, these proofs work with some certain things are fixed and the rest you have to turn into large enough n. So I don't know in which order you have. Okay. Okay. So I wanted to do the other direction. Okay. So this says that one. So this says that 1 minus HP is a natural number to work with, and you cannot, as long as k by n was smaller than 1 minus HP, you can always, there exists some encoding function. It's not as nice as the one which Hamming gave. It's a random function, but there exists an encoding function which, if you send it via this, you can recover without any. Now the question is, next question which Shannon asked is, of course, can one do better than 1 minus h? Thing about Shannon is that no. That's the best you can do, and that's the converse to the coding theorem. And also, let's take the converse also in all this one. So for all binary symmetric channels, for all fudge factors, so long 0 half minus p, if there exists a delta such that if k is larger than 1 minus h2 plus epsilon, so k is larger than this. Suppose k happened to be larger than this, then delta it's a delta n naught, so that all n greater than or equal to n naught. Yeah. So there's a delta. You give me a BSC channel and you tell me how much k is going to be larger than BSC. Then there exists a delta, a noise, then an error parameter, and an endpoint after which the thing is sufficiently large and after which the theorem is true. So that for all encoding and decoding functions, probability that d of they will exist, there exists n such that probability that d of m plus error is equal to m will be less than 2 or minus delta. And this is over the random choices of m. Sorry, this is not over the random choices, only over the random choices of e. E picked from the primary BSC, but no need to. Okay. So this is, you give me a BSC channel and you're going to say you're going to encode slightly more than this one. How much more? An epsilon more. Then I will tell you there's particular error and an n such that if you go beyond that n, no matter which encoding and decoding functions you give me, the probability that the decoding, there will exist at least one message such that the decoding function, the fact that there is the decoding function recovers correctly will be negligible. Almost always it will fail on this message. Okay. So 1 minus HP is a very sharp threshold. For anything less than it, slightly smaller than epsilon, there is an encoding decoding function. For something larger than 1 minus HP, says that no matter which encoding decoding function you have, for every encoding decoding function, this is what is going to be. Okay. The proof of this. Let me refer it to the next lecture. The proof of this is also not hard. The proof of this, once you state it, so both these, the coding theorem and the converse to coding theorem, the statements are ones which are in all gory detail, but the proofs are fairly simple. It's just a bunch of Chernoff and understanding of this binary entropy function. Volume entity will come. I'll sort of give an intuitive idea for the proof, and we'll actually do the formal proof next time. So, let's assume that this is not the case. That is, every message is actually decoded correctly with probability 2 power minus delta n, at least probability 2 power minus delta n. So, what will we show that? So, for every message, the channel adds some noise to it. So, most of it's after the channel you send an E of m. Then what you get is basically the shell around E of m. And what I'm claiming is that, and the shell contains most of the mass. This claim is even among that, with at least so much probability 2 power minus delta n, of it is obtained correctly. That is, there will be, I want to claim there's most of the mass of this particular m lies in the shell, and 2 power minus delta n fraction of it is possibly recovered correctly. This is true for every message. So notice that this 2 power minus delta n in this shell cannot correspond to any other message. This part of it can only be recovered to this message, because the decoding function can't be saying this goes to this message as well as to this message. So there is this small fraction in this shell corresponding to message m, in which you can associate all the points in that fraction to this particular message. And you can do this for every single message. There are 2 power k messages, each of them have these disjoint things. Therefore, the 2 power k into this mass should be less than 2 power n. You will get a contradiction. This is similar to what we did the packing or the Hamming bond. Each of these should be disjoint. You get it, and that will tell you why this cannot be true for every m. They have to be MBMs for which this is. And that's basically we show that for, suppose star was false, then for each m, show that there exists a set, say let's call it T of n, subset of 0, 1 to the n, such that decoding of T of n is always n. When you decode T of m, you will just output n. And so these things are stressed with properties. That 1, this is true, and 2, T of n is large. But then you are this one. That means T of m's form a partition of the at least not a partition, at least T of m are disjoint, because each of them is associated with different m, and each of them are large. So if then this large times 2 power k should be smaller than 2 power n, that will be a contradiction. That's basically going to be the proof. Then 2 power k times large should be less than 2 power n. We'll get a contradiction. Okay. Just a couple of things. What will we do in the next lecture? The next lecture, we will complete this proof. We will compare the Shannon and Hamming questions. Why are they different? turns out that when we actually eventually construct, Shannon talks about randomized channels and stuff. Hamming talks about these worst case errors and stuff. And so we will more or less be focusing on Hamming because there will be more concrete questions. We come with explicit the codes and stuff instead of codes which are just here. In Shannon's case, the code is even for BSC. He gives a says pick this random encoding function. It's not an explicit code at all. We will later on try to see, is there an explicit code that actually achieves? Is there a nice encoding function and decoding function under which you get the capacity for the BSC channel? It will be one of the questions we'll answer towards the end of the course. Compassion, this one. More generally, starting next lecture, for the next couple of lectures, what we'll do is we will sort of put bounds on if a code has to have these features, does the rate and distance have to have satisfy some conditions? We'll look at these things. These are all what are these various bounds called: the singleton bound, the Joshi bound, the packing bound, the Delsart bound. There will be various such bounds. And then we'll also see achievability. What are things that can be achieved? This will be the Gilbert-Varshamov. And we'll see various of these. This is what will be our plan for the next 2 lectures. Is the end of this week or early next week, the first problem set will be out. And even those who are not crediting the course, I would advise you to at least do the problems, even if you don't submit it in, because it will help you get, unless coding, if you don't get your hands dirty, you will there will be the amount of information that will be sent to this one, you will just be passive. Halfway through the course, you will lose track of it. The only way to learn the course is to do problem sets, just to get your hands dirty. So even if this one, so if you are, even if not crediting, if you want to turn in the problem sets, do turn it in, we will grade it. But I would certainly, whether you turn it in or not is not the question, but would advise you all to do the problem sets.